Hello everybody. Today we're going to look at solving trigonometric equations. We'll look at how we solve an equation, talk about how we know how many solutions to expect from an equation. CAS calculators can be used to solve trigonometric equations. We'll look quickly at how to use the CAS calculator properly. We'll talk about how solutions present themselves graphically. And finally, we'll talk about what we mean by a general solution. We're going to start off with a fairly complex equation right at the start. So we're going to solve 2 cosine 2x plus 2 equals 3. There's our equation. This part of the question is asking us to find all the solutions that exist between 0 and 2 pi. I'm going to start by showing you the entire solution so you can see where we're headed to, but I'm actually going to break this down step by step and talk about each step. So starting off, the first few lines of this solution here is just regular doing the same thing to both sides. So we'd like to get to a point where we've got the ratio, the trigonometric ratio by itself. So all I've done here is subtract 2 from both sides of the equation, and then we've divided both sides by 2. We end up with cosine of 2x equals a half. The trigonometric part, the ratio, is by itself on the left-hand side of the equation. The next stage is about using the inverse of cosine, so the inverse ratio, and that's how we're first going to solve for 2x. But this is where our exact values come into solving the equation. We're expected to know the inverse cosine of a half, and not just one solution. So we'll talk about how we find all the solutions for this equation. Originally in the question we're looking for solutions for x, and x is in between 0 and 2 pi. So I find it handy to actually, when we're looking for the inverse cosine, and we're actually solving first what 2x is, if x is in between 0 and 2 pi, by multiplying each part of this inequality by 2, like we have with the middle, that means that the solutions for 2x must be between 0 and 4 pi. And I find this helps me understand how many solutions I'm going to end up with for this equation. So let's have a look at where the exact values come into this. We're talking about the cosine ratio, so we're referring to the horizontal axis of the unit circle. Our exact value is a half, which is exactly halfway along the radius of the unit circle between 0 and 1. So I've just circled a half there, and we are looking for the angles that give us a cosine of a half. Looking at the unit circle, our first angle is going to be pi over 3 radians, and all the way around until we get to the fourth quadrant, our second angle will be 5 pi on 3 radians. Now, these are the first two angles for the inverse cosine of a half, but that's just in one revolution. So from 0 to 2 pi, we are looking for solutions or values of the inverse cosine of a half that exist between 0 and 4 pi. So we actually have to go around one more revolution. And so in the same place as pi on 3, after we've gone around another revolution, we get to 7 pi on 3. And with our second solution, 5 pi on 3, by the time we've gone around another 2 pi radians, another revolution, we come to another solution, which is 11 pi on 3, another value, which is 11 pi on 3. So that will take me to 4 pi. So I've gone around the unit circle twice. So now we can see that we've got 4 solutions to our equation. We're solving for x, and so if my values were for 2x, I've now got to divide all of these by 2, divide both sides of the equation by 2, which means divide every one of these 4 values by 2. In this case, it just changes the denominator to 6, and I can see the 4 solutions for the equation. So even though we found values between 0 and 4 pi on the unit circle, by the time we've divided everything by 2, we've now ended up with 4 solutions that do exist between 0 and 2 pi. 2 pi equates to 12 pi on 6, so 11 pi on 6 comes in just before that boundary. So there are our 4 solutions to this equation. Taking a look at the CAS calculator, if you just use the solve function and you type the equation in, the trigonometric equation, you're going to get an output that looks something like this. That's actually, we're looking at the general solution for this equation. We haven't told the calculator the interval that we want to find solutions within, so the calculator has just assumed that we're looking at the general solution, for which there's an infinite number of solutions to this equation, but they follow a pattern. We'll come to that in a minute. What we need to do, if we're after the specific solutions in this limit from 0 to 2 pi, in this interval, 0 to 2 pi, we need to be able to put that after the solve command on the calculator. So you'll see we've used the solve command. I've got the equation in brackets with the comma and the variable that we solved, and I've closed the brackets, and then you'll see this vertical line, and we've typed in the interval for x. X is greater than or equal to 0, less than or equal to 2 pi. And after we've pressed enter, as you can see, we get the exact same 4 solutions that we did by hand. These symbols, this notation for typing this type of stuff, if we hit control and then equals, it'll bring up a template that looks like this, and that's where we can select those different symbols that we need. It's often very useful to think of graphs while we're solving equations, and vice versa when we're looking at graphs, thinking about solving equations. You can see on this graph I've got the left hand side of the equation that we were solving, which was 2 cosine 2x plus 2, and the red graph, I've graphed the line y equals 3, which was the right hand side of the equation we were solving. And we were looking for solutions that occur between 0 and 2 pi. And so where those two graphs intersect each other, that's where we will have values of x that correspond to our solutions. So there's our pi on 6. We skip over a bit and we get 5 pi on 6. Two solutions quite close together, 5 pi on 6 and 7 pi on 6. And then we skip a bit and we can see we've got a solution at 11 pi on 6. It's worth just keeping your mind on the future and thinking, when would you solve an equation, a trigonometric equation? There's two key times in this course when you'll need to do that. If we are looking for x-intercepts of a function, or zeros of a function, we'll be solving f of x equals 0. Later on, when we're talking about calculus, locating stationary points, we'll be interested in when the derivative is equal to 0. And if it's a trigonometric curve, then that derivative is also going to be a trigonometric or circular function. Let's just talk about the general solution of the equation. Here's the solution that we just worked through. Most of this work is what we do when we're looking for the general solution. So just up until this point here, where I've got pi on 3 and 5 pi on 3, they're two unique solutions, and you might remember that we found 7 pi on 3 and 11 pi on 3 later on. So I call those solutions their values for this inverse cosine of a half. Another way of thinking about two specific solutions would also be to say that negative pi on 3, which is in the fourth quadrant, and pi on 3. The point about this way of writing the two unique solutions to start with is that they're both acute angles, and I think you'll find the calculator tends to use a pair of values like this rather than a pair of values like this, even though both are correct. So let's look at how we take these two specific solutions and then generalize from those to express the infinite number of solutions that there are. Here we've got our first solution at negative pi on 3, that's our fourth quadrant. Any whole number of revolutions takes us to exactly the same place on the unit circle in the fourth quadrant. So here we mean n to be any whole number, including 0, but could be negative, could be positive. So on that unit circle, there's an infinite number of solutions that correspond to the value where x is negative pi on 3. And likewise for the second solution in the first quadrant where we've got pi on 3, there's an infinite number of solutions that exist that are a whole number of revolutions away from that value pi on 3. So 2n pi simply means a number of times around the unit circle, forwards or backwards. It might be necessary to tidy up or to rearrange this expression, so you can see I've expressed both of those terms with a common denominator of 3, and then just rearranging and factorising the numerator. And this is actually very similar to what the calculator gave us before. So 6n minus 1 pi over 6, 6n plus 1 pi over 6. That will be the general solution to our equation. When we express a general solution, it's simply like that. We use that expression. It's important that we specify exactly what we mean by n. N is an element of the set of z, which is simply to say that n can be any whole number, any integer, positive or negative, or 0. So if I was to pluck out n equals 5, by using n equals 5 in each of these expressions, that's going to give me two specific solutions in that solution set. Negative 3, negative 7, positive 8, doesn't matter what value of n is, we'll always get a pair of solutions for each value of n. So just to review, we've looked at solving one particular equation, and we talked along the way about how we can establish how many solutions we have to that equation. We've used a CAS calculator, knowing how to use an interval when we're solving an equation to get specific solutions. Without using that interval, that calculator is going to give us a general solution. We've talked about solutions to equations and how they appear graphically, how we can find them graphically, and we've talked about what we mean by a general solution to an equation. So I'll get you to write down any questions that you have that you need to clarify or to understand better after looking at that lesson. And as usual, I'll get you to complete the Google form, log your attendance, and just check your understanding. Thanks very much.